Good morning and good afternoon. This is Monica Paolini from Sensafili, and today we're talking about machine learning and how machine learning can improve the performance of our wireless networks, which are increasingly complex. And today I'm talking to Tero Rissa. He is the chief architect in machine learning at Nokia Mobile Networks. Tero, thanks for being with us today.
Thank you, and very good to be here.
So let's get started. And can you tell us what is that you're doing personally at Nokia, and what is that Nokia is doing on machine learning in general?
Okay, thank you. So I'm leading the AI ML tribe here in the mobile networks, and we are coordinating the machine learning activities across the organization. So as you might know, we have over 20,000 people here in the mobile networks, and we are ramping up in the machine learning in a accelerated pace. So I have roughly 4 main work streams that we work on, and the first is the AI ML expertise development. So this is a new skill set and also a new mindset that we have to have in the organization corporate wide. So we have a machine learning lead in every N-3 organization, about 200 of them, and then we coordinate the activities in these organizations through this kind of a machine learning center of excellence that I'm governing. And we also then do the training material and training curriculum for the whole organization. Then we are responsible of the AI ML infrastructure management and availability, and this is quite a lot of stuff. So this is from evaluating different kind of acceleration platforms to actually having hosted GPU-based acceleration learning services and capacity for whole Nokia. Then we are responsible of the AI ML data strategy, and this is concerning mostly on the radio access network data across the business units. Basically, data strategy is how to capture, store, and then retrieve the data that is required. And I have to say it's much more complex under the hood than that. And the last, but definitely not least, is then the coordination of AI ML use cases and development and engagement in these use cases with operators, and then developing new business cases and doing this kind of joint labs with operators.
Now, that is interesting because it requires, from what you say, it requires really a big cultural change within the organization itself. It's not just a new product that you add. It's more a pervasive change that you have across the company. Is that right?
That's absolutely right. And actually, when I do these trainings, for example, I often say that the hardest part to understand or learn in the machine learning is the actual mindset, what it can solve and how it can solve, and what it means when you do something with machine learning. It's not a partial derivatives of the gradient descent backpropagation. It is actually to understand what you can do and how you have to approach systematically gathering the data and gathering the training material for the machine learning algorithms. So very much yes.
Absolutely, yeah. You're trying to do the same things in a different way, so that's more difficult than just learning to do something new in an isolated way. Now, you talk about AI and machine learning, and that's something that different people mean different things. So what is AI and machine learning to you?
So for me, I try to use machine learning as often as possible. It is still reasonably vague term in a way, but it can be then reduced to certain algorithms that are commonly understood, and especially in this case, we referring to deep learning methods like supervised learning, reinforcement learning, and unsupervised learning. And then AI is often used to refer these, but is also often used for something that I don't believe exists, like general machine intelligence or self-aware systems or superhuman intelligence or whatever that could be. So I really try to move the lingo from the artificial intelligence to machine learning, that it would be much more tangible. And I think there is a lot of hype, and also this hype is not only making that people don't know what machine learning is or AI is, they also then have a wrong kind of understanding that this is this magic that happened, that I have this problem that I can't even formulate, but could you go and use AI to solve it? So my life would become easier. And it's definitely not that. So my kind of common answer is that this is automation. Machine learning is automation of decisions. So if you have a decision that you know how to make consistently millions of times, but of course human power can't be used to do those decisions in real time, we can use machines now to make those decisions for you in automated fashion. And that already narrows down the scope of the AI so much that typically is helpful for people to understand the problem.
Yeah, this is very refreshing to hear, because I think you want to be realistic so that you don't have set your expectations so high that you're going to fail because you're trying to do everything. And obviously there is not magic. It's a lot of hard work, as a matter of fact.
No, actually my training materials title is machine learning. Machine learning is not magic. Practical approach for applying machine learning in an industrial context.
Yeah. So and you mentioned hype. So let's go back to why now? Because yes, you can say that there is hype, but why is the hype now? Why wasn't like 10 years ago?
Well, there was a hype 10 years ago. Okay. So I was actually doing machine learning or artificial neural networks, as they were called at that point 10 years ago. And I stopped roughly 10 years ago and decided it's not going anywhere, and changed my career to go other direction. But now I came back, and the question is why now? And there are three distinct things that has happened in the past 10 years. The first one is algorithms. So the solid foundation of deep supervised learning, and in particular, for example, stochastic gradient descent and reinforcement linear unit activation, they just so much more practical and enable much, although very simple as a mathematical, but as a applied method, they enable much deeper networks to be trained. And then on algorithmic front, we have so vast amount of research going on that 10 years ago, no matter what kind of resources you would have had, you can't outpace that amount of research. So there's a really good community and bag of tricks you can pull from the academia. Then the frameworks have improved vastly. So if you had to do something with artificial intelligence or neural networks 10 years ago, it took you several months to achieve the same amount of result that it took that now it takes an afternoon that you have 2 coffee breaks. So they're like Keras, TensorFlow, PyTorch, and also like other things related like Docker and then acceleration libraries from the vendors. It's just dramatic increase in productivity. So you can do much more. You can achieve much more in a shorter amount of time. Then the final nail in the coffin 10 years ago was the computational capacity. So we were off about, I was doing mobile phone context, so we were off by 10,000 times the performance requirements and memory requirements of mobile devices of 10 years ago. And now we have moved from few giga operations to hundreds of tera operations per second that is achievable. And most importantly, we have moved to multiple teraops per watt energy efficiency. And also what I see really important and is a big part of the work we do here is then the reduced bit width architectures that are dedicated, I would say dedicated architecture for machine learning. So far machine learning has been done with devices that are capable to matrix multiplication in accelerated fashion, but now we are seeing an emergence of devices that have special hardware architectures that really address the needs of machine learning much more specifically.
Yeah, so how do you get it right? Because clearly there's a lot of work that needs to be done. You want to do it right, move in the right direction. What do you think is the best direction to move forward?
Can you clarify on which front? I mean,
within Nokia and in general within the industry, what is that we should realistically expect? What is it we should go for? What is it we should go for initially? What is the realistic goal to achieve?
Yes. So I mean, how to apply machine learning in industry? So yeah, we have actually really pragmatic approach for that. So it's not agreed by everyone, but what I have said that every unit's first machine learning project should be about supervised learning. So basically it restricts the scope a lot, but it's something that we have had heated debates on. That, for example, reinforcement learning, you wouldn't need that much of training data, but it's much harder paradigm and it's much more fragile. So if you get supervised learning system working in your system, you have to also then bite the bullet and acquire the data to train your networks, and you have to do the legwork, and you do have to do the frameworks and the integration. And what we take an approach is that we do first supervised learning machine learning systems deployed that are actually very practical. They have meaningful difference, that they improve something in the system, but they don't change the whole system, and they don't take over the world. But I think for us, the approach is that we do a simple and manageable sized task first with machine learning, and it doesn't so much. It does matter, but it doesn't so much matter what the application area, the use case is, as long as it improves the system, and we can show that there is a cost benefit of doing it. And there's so much other things that you have to take into account than the actual algorithm, the machine learning algorithm. And if you start with too big of the core, then the whole cake becomes too big. So if you start with something that is simple and slam dunk from machine learning point of view, you very well will find out that the other things are required are very demanding. The software integration parts and the data acquisition parts and the data engineering, the infrastructure. So in a way that what we try to say that the best approach is to make sure that your first machine learning project is successful, not that your first machine learning project changes the world.
Yeah. So you try to move first, and but at the same time, networks are becoming more complex, and so how can you deal with that? Is it are we just going to have, is the complexity such that it's going to be challenging, or how do we deal with that?
No, I think these are tied hand to hand together. So we have to cover all the technology generations. So 2G is still there, and we're introducing and deploying now 5G. It takes surprisingly small amount of time that 6G is there, maybe 10 years. And each generation is more complex than the previous. And true complexity actually arises from the requirement that we have to support this generation at the same time. So we have to have all the G's, if you may. And the permutations of different configuration parameters on these systems alone is just becoming unwieldy for human to manage. So we do need machine learning. And also we need to aspire for full automation of the networks. So the business benefit, the main business benefit for the networks comes from the operational cost optimization of running the networks. but also then that while we are using machine learning in these networks, we can actually optimize so that the individual network element is customized to be specific to its operational environment. So machine learning, it doesn't come, that is also sometimes misunderstood. Machine learning doesn't bring that automatically. You have to work for it, but you can do that. The environment itself trains the network to be specific to the operational, where the actual radio element is situated. And it can, with this we can achieve significant benefits in the network. So first of all, we need it, but then also we can have a lot of leverage on there. And business point of view, as I said, the optimization of operational expenditure is through like advanced automation is actually one of the main things we can achieve. But we can also deliver a better user experience in cost-effective manner, which is basically the same thing said in a other way, that we reduce cost, but we increase the benefit, and basically deploy the radio spectrum in a more efficient way. And we can also then have energy savings, and we can have increased security and resilience for intruders, for example.
Yeah, so there is a lot of benefits. So you can optimize in real time, and it can be specific. But what that means is that in order to do that, it's not just, you don't learn something just for the network, you learn it for a specific location. How to act, to react to network conditions that are changing, demand that is changing. And that brings the question of where is the learning going to take place within the network? Is it going to be in a centralized location, in a distributed location? Is it going to be at the edge? And if it's towards the edge, where in the edge is going to be?
It's really good question that we don't have a final answer yet, ultimate answer, but the starting point for us that we will have a centralized training approach. That's because we know that approach works for sure, and we can move towards the edge in the coming years. But we will start from the training, and this is also driven from the point of view that what we see is that you do require different hardware acceleration for the training and for inference. So even if you would do the training in the edge, it could be that we still need different hardware for that, and that wouldn't just make any sense, and it wouldn't be cost effective to do so. And inference rate we can do in some cases millions of inferences per second, but the training would rarely be more frequent than a second. Even a day cycle is very common. But anyway, the inference or the utilization rate is so vastly different. And also, we do see, as I mentioned, this reduced bit architectures, that we see that in inference, the non-floating point architectures will dominate, or we will require those. So there's 100 times difference between a 8-bit add and floating point add, for example, in the silicon real estate. And also then on the training side, at this point, we see that floating point is still very much required. Maybe not full, but for example, B floats looks quite satisfactory in that context. But anyway, the hardware is different, the cycle is different, the bottlenecks are different. So it's better to start the approach with centralized training facilities and then distributed inference.
So you start the initial part of the learning is centralized, and you kind of spread it out.
No, also you come back then to, you gather the data in the locality, but the training itself, even if the data has to be transported, is then happening in some centralized environments. Of course, we don't have to have one globally, but in a way that they are less distributed than the inference engines are.
Absolutely. So you can benefit from the sort of centralized learning and then apply it to different environments.
Yeah. So in what is not typical for machine learning projects, I believe elsewhere, or not so typical, that most of the companies can take networks that are ready-made, for example, image and voice speech recognition and processing. For radio networks, unfortunately, the situation is not such that there are vast number of ready-made networks. So we have very early on accustomed of doing our own networks and training our own networks. And also, even if we do centralized training, even the network topology or the architecture can be very custom to the actual problem or actual data that network element is seeing. So I think that's something that we might do a bit differently than rest of the industry, that we see the training as, well, I speak about training, but I also mean the architecture exploration at that point.
Absolutely.
Even if you have the centralized system, we can still deploy completely individual networks and completely individual training for each element.
Mm-hmm. So if we look at sort of in terms of the sort of low-hanging fruits, what are the best use cases for machine learning in the sort of like more in the shorter medium term?
Yeah, so I would say that we have, again, 4 different categories that I can't pick what would be the most beneficial, but definitely what we're looking in. The first one is to use machine learning actually in the making of the radio networks, so increasing productivity. So, for example, passing the compilation or SOC tool flow logs and have a code review automation and automated training or software robotics there. So just using machine learning to improve the production of radio network infrastructure and chips and the deployment and so forth. Then I think what everyone would think is the main thing is the radio technologies itself. So radio algorithms. So there we have a lot of use cases that basically just improve, for example, radio resource management or massive MIMO scheduling, or have exactly this energy-aware scheduling. So how the technologies are themselves better. Then really obvious one, and if I would need to pick one, is the most exciting and there's most to gain, is then the actual running of the networks. So self-organized networks, and they have the performance capacity prediction, and they're the OPEX and CAPEX savings come into play. So all this predictive maintenance and automated configuration, optimization, and fault detection and recovery, and also the security management and resilience that I mentioned earlier on. So I think in the running the networks is a huge thing that will change, I think, the most of the things. The radio technology ones are very good, and exciting. However, you never see them, you never feel them. They just work better, but you don't actually see them. But if the network actually works and recovers itself, you can actually physically feel it. Then the last category is the user plane edge computing. So what we already have is the most distributed computational platform with our networks, and the base stations are becoming more and more server-like, where we can then now start deploying machine learning capabilities. So in this edge computing case, or edge cloud computing case, we could also utilize the machine learning capabilities for third-party applications. And this is something that I feel that is something that happens no matter what, because of the latency of the inference pushes the applications towards the edge cloud servers, and then the energy efficiency pushes them out from the end terminals. So they naturally converge in this edge cloud. to be most efficient to be implemented.
So there is a lot that machine learning can do. So let me ask you a final question. We sort of like goes back, because when a lot of people get so excited, it's all great, but there is also at some level the fear of the black box surfaces, and so people are like, yes, we see this might work, but how do we trust it? We don't really understand it.
Yeah, and it definitely is the one of the most important things that, for example, my group is doing academic collaboration with, how to increase the understanding and how to make the machine learning systems more an engineering and not an art, that you have just to try stuff and see how it works, how you can actually deduce that what went wrong and then make a logic steps that makes it better. And I believe this is something we really have to take into account and look in the future. So currently, I see that is actually one of the biggest things preventing some use cases from being done with machine learning. And I think it might be that some of these use cases where you can't have any errors ever can't be done with machine learning. So I think in the first steps, before we have this kind of more engineering approach, we have to approach in a way that assume not that your machine learning system is 98% right. Start from the point that your machine learning system is 2% wrong, and build that into your system and make the resiliency of the application. And then this interpretability and explainability of the machine learning systems hopefully catches up and comes. And it's still a very much, I think, research topic, how to advance in there. And what we have seen that the best method there is very engineering method. So break down your problem. Don't have a huge end-to-end network, but actually do separate tasks with different networks. So it actually then brings back to a system engineering, how you divide your task and how you have different networks doing different things. And in the end, the network of the networks is actually more predictable, and you can have some kind of error bounds that you know can happen in that system.
So it looks like we have to learn too. In order to get the machines to learn, we have to learn to do things differently as well. So it's like it's a mutual process.
Absolutely.
It's not, and I guess it's a long-term and continuous one as well.
Yes, absolutely.
Well, Tero, thanks for sharing your thoughts with us today. It was a pleasure talking to you.
Thank you. It was a pleasure for me as well.
And thank you all for listening in. This was a conversation with Tero Rissa. He is the chief architect of machine learning at Nokia Mobile Networks. And this is part of a report on AI and machine learning from Senza Fili. Thanks a lot.